discuss proposition 5.7. In this theorem, we discuss the equivalency of the statement A divides B if and only if A contains B. So first we can prove A divides B implies, by definition, there exists a C, an ideal C, such that this B can be written as A times C. This is the definition of A divides B. From this you can write, this implies A contains AC, right? Because if you consider an arbitrary element of AC, then that element takes the form summation I equal to 1 to n AI Ci, where AI comes from this A and Ci comes from C. Then this product, each element can be considered as an element of A as well as C. Okay? Because A is an ideal, then this product is always an element of A. So each element is an element of A. Okay, so this is an element of A itself. So we can say that AC is a subset of A itself. So A contains AC. AC is nothing but B. So whenever we have A divides B, this A contains B. Okay, this is the first implication. The second implication, once we assume this A contains B, we need to prove that A divides B. Okay, from this you can write O is contained in A inverse subset of B inverse. Okay, when you take the inverse, we can get the reverse inclusions. Then by multiplying with B, we can get BO is B itself. It's a subset of B A inverse subset of B inverse. That is again O. Okay. From this we can say that this is a fractional ideal which is contained in O. Hence it is an ideal. So this implies B A inverse is an ideal. Okay. Therefore, you can write B as B A inverse into A. Okay. Then we take this as C. Say this is C. Then B can be written as C times A. So from this you can write this A divides B. So this proves proposition 5.7. A divides B if and only if A contains B. Therefore, the meaning of this result is whenever you consider the factors of an ideal B, say A, then that A should contain B. That means all the factors of B contains B. So in order to get the factors of an ideal, we need to consider the ideals that contains this B itself. Here we have an exercise. We need to find the factors of ideal generated by 18 in Z of root minus 17. So in order to get the factors of 18, we need to find the ideals of Z of root minus 17 which contains this ideal generated by 18. For that we first write 18 is equal to 2 into 3 into 3, and 18 can also be written as 1 plus root minus 17 into 1 minus root minus 17. Now we define an arbitrary ideal P1 that is ideal generated by 2 comma 1 plus root minus 17. So it contains all the multiples of 2 and 1 plus root minus 17 and the combination of these two. So obviously this 18 is also an element of this ideal P1 because 2 into some 9, okay, that is also an element of P1. So that is 18, so 18 belongs to P1. On the other way we can write 1 plus root minus 17 into an element 1 minus root minus 17, that is also an element of P1. Therefore 18 is also an element of P1 in that way. So we can say that the ideal generated by 18 is always contained in P1. Okay, so which means that P1 is a factor of 18 because that is the equivalent condition. A divides B if and only if that contains A contains B. So here we can say that P1 contains ideal generated by 18. Then we can say that P1 is a factor of 18. Using this idea, we can find the factors of 18, hence, we can get the factorization of the ideal gender by 18. So, you must go through this methods how to find the factors of ideal gender by 18. So, finally, you can get this ideal gender by 18 is nothing but this p1 square p2 square into p3 square. Okay, fine. This is the final step. So you must go through these procedure how to find the factors of ideal generated by 18. So the key idea using to find the factors of ideal generated by 18 is the previous theorem. Okay, A divides B if and only if A contains B. Now we will define a norm of an ideal. A norm of an ideal P is defined as cardinality of O by P. This is the cardinality of the quotient ring O by P. Then we have this property n of AB is equal to n of A into n of B. We will prove this theorem. We will prove this result as a theorem later. But we use this n of A equal to n of A and n of B, this property, multiplicative property, to discuss the factorization of ideal generated by 18. Using that fact, you can see this ideal 18 can be written as 2 into 3 square and product of two ideals like this 1 plus root minus 17 into 1 minus ideal generated by 1 minus root minus 17. The next uh, section 5.3, we will discuss the norm of an ideal in a classical way. In this section, we will prove the property of ideals as multiplicative property of the ideals. Before going to study the properties of the ideal norm of an ideal, we will define a greatest common divisor and least common multiple of two ideals. This is the consequence of the prime factorization of ideals. So G divides A. This is the definition of the greatest common divisor. G is said to be greatest common divisor of A and B. If G has this property, G divides A, G divides B, and G dash has the same, and if G dash has the same properties, G dash should divide G. Okay, so this G will be the greatest one in some sense. To define least common multiple, say L has this much property. A divides L, B divides L. Whenever L prime divides L, then whenever L prime has the same property, then we can say that L divides L prime. In this sense, we can say that this L is the least multiple of these A and B. To evaluate the GCD and LCM of two ideals, we need to find out the prime factorization of A and B. Say A is equal to P1 raised to E1, P2 raised to E2, etc. Pk raised to AK, powers of prime ideals. Then B has an expression like this. Then G is defined as Pi raised to minimum of Ei comma Fi, and L is the maximum of Ei comma Fi. So these are the definition of GCD and LCM of two ideals A and B. Now we can prove lemma 5.8. If A and B are two ideals of O, then GCD and LCM are the greatest common divisor and least common multiple. Then this G is nothing but A plus B, and L is least common multiple is A intersection B. This is using the proposition 5.7. In 5.7, we have proved that A divides B if and only if A contains. Divisibility is nothing but the containment of this A. A contains B. Now, if you use this, you can easily we can easily prove that this G satisfies the condition for, or A plus B satisfies the condition for greatest common divisor. That is, A plus B contains A plus B contains B. So from these two statements, we can get uh, this a plus b contains a can be replaced by the divisibility, so this a plus b divides a, a plus b divides b, so this is a common divisor of a and b. Now, whenever any ideal G prime divides both A and B, from this you can, using this inclusion, we can write G prime contains A and G prime contains B. Whenever G prime contains both A and B, then G prime contains A plus B as well. So, using this, G prime divides this A plus B. Okay, so we can say that this a plus b is the GCD of this a and b. In the similar way, you can prove that this a intersection b using the inclusion, because a intersection b, a contains a intersection b, b contains a intersection b. So we can say that a divides a intersection b and b divides a intersection b. Okay, using the same facts, you can prove that this L is the least common multiple of this A and B. So whenever you are given two ideals A and B, you can easily write this is the GCD and this is the LCM of two ideals. So this proves lemma 5.8. In the proof of theorem 5.3, we already proved that this O by A is always finite. Okay, using the quotient rings, we have proved that this is always finite. So this finite number, cardinality of this O by A is defined as norm of A. Okay, therefore this no n of any norm of any ideal is a positive integer. So we must remember one thing, this symbol n of a, if we write a here, then n of a is always a positive integer, and it referred to the norm of a ideal, and it is the cardinality of some quotient ring. When you write this n of a like this a, if a is an element, then this defines norm of an element. That is the product of the monomorphisms.